My name is Tomislav. I come from Zagreb in Croatia, and I'm talking about mathematics in motion. So first, what is motion? Motion is a change in position of object with respect to time and its reference point. It is described with functions in terms of acceleration, speed, velocity, distance, and time. Goals of this project. I want to study and analyze examples of motion, and I want to describe and explain motion in each example. Examples include juggling basketball, cone rail demonstration, perpetuum mobile train, and drift. So first, juggling. Juggling is a skill involving manipulation of objects. In juggling, objects are thrown into the air and then caught again. It's performed by a juggler, and it's done for art, entertainment, sport, and so on. Juggling sequence. So juggling sequence represents some juggling patterns. Not every juggling is the same. In every juggling pattern, juggles to a certain beat. So with juggling sequence, describe each pattern. So every ball stays in the air for a certain amount of beats. In basic pattern, no matter how many balls, every ball stays in the air for the same amount of beats. For example, 555 is a basic pattern, but 501 is not a basic pattern because yes.
What does zero mean?
Okay, zero means that at that moment no balls are thrown or caught. So in this sequence, juggler uses two balls. 501 sequence is the same as sequence 150 and 015, but not every sequence can be juggled. And to check if a sequence can be juggled, use a juggling diagram. It's a graphical representation of a juggling sequence. It must be long enough so it could capture the periodic nature of that sequence. And sequence can be juggled if a diagram extends indefinitely to both sides, and if on every beat, so this is timeline, beats, if on every beat at most one ball lands and gets tossed again. As we can see, the sequence 2-1 can't be juggled because at here two balls land but one gets tossed. So one would have to just vanish, and that's impossible. But sequence 501 can be juggled. As you can see, it extends indefinitely to both sides, and on every beat, one ball, at most one ball lands and gets tossed again in the air. Now, if you don't want to draw, you're afraid that you would draw incorrectly, use mathematical juggling checker. It's a method with which you can check if a certain sequence can be juggled. I'm going to demonstrate it on an example of sequence 3441. So period of this sequence is 4. You will form a second sequence which has the same period but consists of consecutive numbers starting from 0. So in this example, the second sequence is 0, 1, 2, 3. Now we form a third sequence by adding elements of the first and second sequence together. So in this example, 3 plus 0 is 3, 4 plus 1 is 5, and so on. Now we form a test sequence whose elements are the remainder of the elements of third sequence when they are divided by period. So 3 divided by 4 gives us a remainder of 3. 5 divided by 4 gives us a remainder of 1, and so on. And now if all elements in the test sequence are different, then the sequence can be juggled. So if you remember the sequence 2-1 can be juggled, we can try this method and that sequence too. So period is 2, so second sequence is 0, 1. Third sequence is 2, 2. When divided by period of 2, 2, you get reminders 0, 0. So 0 equals 0, so that sequence can't be juggled. Now, juggling video analysis. I recorded my friend as he juggled 3 balls in a basic pattern, and then applied video analysis on that video. So I expect the parabola to be the trajectory of the ball to be parabola given by this equation. H represents height in meters, T represents time in seconds, and A represents accelerations in meters by second squared. We expect that the acceleration will be around minus g when g equals 9.81 meters per second squared.
H0 is the height of the head?
Yes, H0 is the starting height, and V0 is the starting speed. Yes. Now I'm going to show you the video. Okay, so here you can see my friend as he juggles. These points track the ball. Here you can see, now I can go to the data tool. Here I can fit the parabola to this data and get its equation here. And now, from that equation, we get that g is 10.47 meters per second squared, and when compared to the known value of 9.81, that gives us relative error of 6.69%. Okay, basketball. In basketball, you all know objective is to shoot the ball through a hoop. Trajectory of a ball is parabola, and the player aims for the parabola to pass through a hoop, so the ball would pass through a hoop and he could hit points. So again, the equation is the same. H represents height, T represents time, and A represents acceleration. And we expect that G will be around 9.81 meters per second squared. Now I'm going to show you the videos. In this exam case, I again recorded the same friend, but this time I used 3 videos in the analysis. So this is the first one. The second one. And the third one. Now we can go again to the data tool, and for each video we can fit the curve in here, parabola, and get its equation. And when using these 3 equations, here's the second one. Here's the second equation and the third equation. Okay, and by using these 3 equations, we get 3 values for the G. When we take the average of that, we get 9.80, which is a relative error of 0.1%, which is great. And so here we can see when we use 3 videos, not just one, the value is much more precise and closer to the real known value. Okay, unexpected motion. So we all know what's motion, but unexpected motion is a motion in which an object moves different than you expected. Examples include cone rail demonstration, perpetual model train, and drifting. Now, cone rail demonstration, I have a model of that here. I'd like to show it to you now. So you probably already saw this demonstration, but you know what happens. So I put the cone, as you can see, this end is lower than this one. I put it like this, and I put cone here. It moves up, which makes no sense, because as you all know, everything moves down. So why does that happen? Well, why do things move? Things move towards the center of the Earth because of Earth's gravity field. In other words, everything moves towards ground. If I let this go, it goes towards ground. So if we divide this demonstration in 2 parts, part 1 would be as rail's height increases, as you can see, the cone's height actually increases also. But as rails are getting wider, and because of the angle here, the cone gets down. If the rails were the same height, but just getting wider, the cone would be getting down.
Would be down.
Okay. Now, I told you already that everything moves towards the center of the Earth. So that means that cone should actually be getting lower. And here we divide it in 2 parts. As in the part 1, cone's height increases, but in part 2, cone's height decreases. So for this demonstration to work, cone must lower more because it rail's widening, then gets higher because it rail's rising. Okay, here you can see a sketch of the double cone here. This is the B represents the base. Both cones are the same, they're symmetrical. VP represents the height of the cone. Okay, and now if we mark delta a big H, the change in cone's height because it was getting wider. We know that delta big H ultimately has positive value. It's the amount for which cone gets lower. And this is the formula by which you can calculate it. Delta Zx is when you put a perpendicular line to this, going to the center, you measure the change from distance of that line to one end here, which is 0 in this case, from that line to here. That is delta Zx. When you multiply that by base and divide it by 2 times height of the cone, you get delta big H. Now, delta small h, you can measure it. That's for how much the height of the rails on both ends is different. It has to get lower more, and it's getting lower for the delta big H value, then it is getting higher for the delta small h value. So for the demonstration to work, delta big H has to be larger than delta small h. Okay, perpetuum mobile track. So it would be based on the same principle as this. You'd have these two cones, but in the center you would have a carriage. And you have these cones here. You would have tracks like this, one after another, a few, and the train would go just by itself. If it would have some obstruction on its way, when it would be removed, it would just continue because of gravity. So if that would work, we would have trains like that today because that's free energy. But it wouldn't work. So here are some sketches that were made before around 8 years, I think. So in this sketch, you can see the surface area of the area in which rail and cone are touching is too big. That would cause too much friction. And as cone is actually getting lowered a bit, and then it would get higher when it would come to the next rail. And it would be going down, up, so that would be very uncomfortable travel. And lastly, drifting. So drifting is a driving technique. In it, the driver intentionally oversteers, and that causes loss of traction in rear wheels or in all tires. But despite that, driver maintains control from entry to exit of corner and doesn't crash most of the time. So slip angle. First, what's slip angle? Slip angle is this the angle between tire actual path, so path that tire will go, and the tire center. So when you turn the tire like this on a car, it doesn't go like this, it goes like that. And the angle between these two lines is slip angle. On street cars, it is generally around a few degrees, 3 to 4 degrees. On the racing cars, it's bigger, but on the drifting cars, it's the biggest, around 40 degrees. Okay, and oversteer. So oversteer is when slip angle of rear tires is greater than slip angle of front tires. So in this demonstration, this sketch, a car would go with this green line if it would go normal. When it oversteers, it goes like this. And that's how it looks when the car is oversteering. But in drifting, car doesn't go out to the track because of large slip angle. Okay, so a program used for video analysis is Tracker. It's an open source software part of open source physics project. And I'd like to thank Marin Tejic for juggling and playing basketball and for allowing me to use that footage in my project and showing it to you here. And I would like to thank my teacher, Eva Šparil, for help in this project. Thank you for your attention, and I hope you enjoy.